All right, looks like I've gotten the green light to go, so go ahead and get started. Welcome everyone to SQL Server Transaction Log Internals. My name is Tim Chapman. Before we begin, let's see a show of hands. Who here are coming from the database development side? So a large majority. Okay, what about DBAs? Oh, okay, larger majority. So, excuse me. So we're going to talk about today a little bit from both aspects in terms of development and how you can make your transactions faster in terms of how they're written to the transaction log, but also from the DBA perspective, what's going on under the covers whenever transactions are happening and what's happening in the transaction log in terms of SQL Server internals. So we'll look at it from both aspects. About me, my name is Tim Chapman. I work for Microsoft as a PFE. I'm a dedicated support engineer, which basically just means I have a set of dedicated customers that I work with all the time. I was a contributing author to 2 different books, the 2012 Bible, and before I came to Microsoft, I was a SQL Server MVP. So I contributed 1 chapter to the last MVP Deep Dives book. I am a SQL Server MCM, which basically means I know quite a bit about a little bit of SQL Server. It's a huge product. I am on Twitter. My handle on Twitter is Chatmandu. I was told before the session began that the demos, this is going to be a pretty demo-heavy talk. The demo scripts won't be available through the TechEd website, but if you message me on Twitter, whether it's a DM or just a regular message, I'll try to figure out a way to make these scripts available to you if you want to go and download them and play along. So today's agenda, I'm going to start off by talking about how transactions work inside the database engine. We'll look at that first, and then we'll kind of switch over and look at the actual internals of the transaction log file. So look at a database file overview first, and we'll talk about logging and recovery, and then eventually we'll get into the actual internals of the log file itself. During the talk, so this is a 75-minute talk. The suggested format is I go 60 minutes, and then we leave questions for the end for 15 minutes. If you want to ask questions during the talk, feel free. I'm happy to answer them during, or we could just leave questions to the end. If no one asks questions, I have plenty of demos to keep you occupied with, so we should have plenty of time. We'll have enough content to fill up the 75 minutes. So, but feel free to ask questions while we're playing along here. So database files. Database files are where your data lives. The main thing that I want you to take away from this talk about data files is the fact that we write to the data files only after we have written to the transaction log file, regardless of the scenario. So anytime you write a record to the database, you update a record in the database, you delete a record, we're writing to the transaction log first, and then later we're going to go and we're going to update the data files. A data file itself always belongs to a container object known as a file group. By default, SQL Server has one file group known as the primary file group, and all object data is placed in the primary file group. I'm going to suggest to you that in terms of administration, you should have at least 2 file groups and preferably more. This gives you a little bit of flexibility in terms of where you put your file groups on disk, but also it gives you options for restoring your database in a piecemeal fashion should you ever have to do that. You have to architect for such a design, but it does allow you to, for example, if I have a disaster and I have a huge database and I only care about bringing my most relevant, maybe 2013, 2012 data online, I have the ability to bring that data online and leave my older data offline. So I do have that ability as a DBA, but I do have to design for it. Reads and writes to the data files are random in nature. Our data is distributed in many different spots in our data file, and to go and pull that data into the buffer pool, we have to go out to disk to read it, and it's always usually in a random spot. So our disks stay very busy as our data files are concerned. But again, the main thing to take away here for data files, changes occur to our data files only after we have written transactions to the transaction log. Transaction log files. These capture the state changes in our database. So anytime we create a new table, a checkpoint occurs, we write a record to a database, we delete a table, we truncate a table, any change that changes the state of the database, we have to write log records to the transaction log file. So think in terms of abstractness as the transaction log is essentially a table. It obviously is not a table, but anytime we change anything, we have to write a record to this table to essentially indicate what has happened. We keep track of what has happened, and we keep enough space in the file to be able to undo a change. So the transaction log file itself implements 2 different of the 4 transaction properties. Does anyone want to guess what the 4 total properties are of a transaction for bonus points? Any hands? No one ever raises their hands, right? It's okay. So the 2 properties that the transaction log file implements is the atomicity and the durability properties. The other 2 properties are isolation and consistency. I'll talk about atomicity and durability in the next slide, but isolation, a property of a transaction that ensures that one transaction can't interact with another transaction. SQL Server, we implement that through locking. Other RDBMSs do it through optimistic locking, row versioning. SQL Server has an ability to do that, but by default, we use locks. Consistency says that once a transaction completes, it will leave the database in a consistent state. So if you write a transaction in SQL Server, you should not have the ability to corrupt a database just through a simple update delete statement. So that's the consistency property. Transaction log files are always written to sequentially. That means you never need more than one of these. You absolutely have no benefit by adding more than one transaction log file to a database. There is a caveat to that in that if my transaction log file is on a drive that's filled, so I'm completely out of space, I can get away from my database being shut down if I add an additional log file to a different drive. Because if my log file is on a data drive or SAN drive and it's out of space, SQL Server can no longer write transactions to the file, which means that since I can't write transactions to the file, my database is offline. I can no longer service requests. So where should we put our transaction log file? It kind of depends. Most of the things I talk about today in terms of the SQL Server world comes with a caveat, and it depends. It's all relational specific, right? Or scenario specific. Usually, on its own LUN, whether it's on dedicated disks or on a SAN, is a good start, just because it gives you the ability to segment where your log file is coming from. And that benefits you if for no other reason than if I'm looking at perfmon and I want to look at my average disk seconds per read, average disk seconds per write, my latency, it's easier for me to discern if I'm having problems writing to my log drive if it's on its own LUN. So for no other reason, just for manageability purposes. From a SAN perspective, it's a little more difficult to know that your log file is on its own set of dedicated disks. You have to have a SAN guy carve those out for you, and sometimes that's a problem. But its own LUN's a good start. If you have a very high throughput system, having it on its own set of disks is maybe necessary. Not always, though. Okay. Especially if you have several databases on a system and they are all sharing the same set of dedicated disks. So even though so the knowledge out there is that you should always segment your data files from your log files, right? Because you don't want your random reads and writes mixing up with your sequential reads and writes. However, if I have a LUN carved out and I have all my log files on that same set of disks, my drives aren't writing to those files sequential anymore because those drive heads are servicing all those log files. So my intent to segment them so that I'm able to service those sequential reads and writes, it was a good thought, but however, my drive heads are having to surface all of those log files, so it's more random in nature now. It's rare to see problems come from that, but if you have a very high throughput application that's really writing to your log, hammering your log drive, then you certainly could get gains just by making sure that you're segmenting your 1 or 2 very busy log files from other files and having them on their own set of drives. You don't want your log file drives to fail, because if your log file drives fail, your database is down. So redundancy is your friend here. So RAID 1 or RAID 10 provides a good set of redundancy. You want to stay away from RAID 5 just because of the write overhead with putting it on RAID 5. Okay? Data files, it more depends on your style of application. And this depends as well, because if I have databases that aren't bound by I/O, so if I'm not having a problem writing to my log file drives, then it doesn't really matter if it's on RAID 5, it may not matter. But the more needy my log file drives are, the more gain I'm going to get by segmenting them onto their own disks and having them on probably RAID 10 and away from RAID 5. Keep them away from other files? Yeah. Right. So the question was, today we have SANs and we have a lot of cache on our SANs, and is this important? And the answer is maybe. Because, and I'm going to talk about the write-ahead logging protocol. And the write-ahead logging protocol says we have to write to the transaction log file, and it has to be durable on the transaction log file before our data file can be written to and before our transaction can commit. If I have a SAN that is compliant and I can write to that cache and it's battery backed and it's durable, then yes, that matters less in terms of writes, because as long as it's battery backed, then I'm okay. But if I have to write to disk, then yeah, it still applies. Great question. Any other questions? So bringing a database online. Whenever I bring a database online, whether my database is offline and I just right-click and bring it online, whether I have a cluster failover, whether I have to attach a database, whether I restore from backup, we have to go through a series of operations that basically bring the database to a consistent state. The log file is the main component of that bringing the database online, because the log file contains all the information that is necessary to bring the database to a consistent state. If the database is in a state of flux, so if I'm still servicing transactions and I take the database offline, I could have transactions that are still not committed, so I'm going to have to roll those transactions back. I'm going to have transactions that have been committed but not yet reflected to the data files, and so there's work for me to do there. So we go through a series of steps to put the database into a consistent state. This is known as recovery. And we have to run recovery when a failover occurs for a cluster, whenever we just bring the database online, when we restore from backup. Any of those steps brings the database to a consistent state. Here are the three phases of recovery. First is the analysis phase. And for the most part, the transaction, 100%, the transaction log is a part of all three of these phases. The first phase is the analysis phase. In the analysis phase, we're reading through the transaction log, and we're finding basically the place where we can start reading and determine the transactions that need to be rolled back and the transactions that need to be committed. So as we start at something known as the last checkpoint, and from there, we'll build an in-memory representation of transactions that are committed but not yet reflected to the data file, and transactions that are still in flight and we have to roll back. Okay. Anytime we commit any type of transaction in SQL Server, a few things have to occur. Number one, we have to make sure that the data pages, all records exist on data pages, 8K pages, and we have to make sure that they're in a portion of memory known as the buffer pool. Any type of data modification that occurs, we always have to make sure that we change that record in the buffer pool first. Once we've changed it in the buffer pool and it remains in the buffer pool, it doesn't matter if that change has been reflected to disk yet or not, because we've written log records to the transaction log file that indicate the change that is made. That if we need to read that page again, we've already got the page in the buffer pool, so we'll have the most current version of the change. The problem is that after a while, as we accumulate more and more pages that have changed, we can't keep them all in the buffer pool. Our buffer pool is usually finite. Even servers today, they have more and more memory, but it's finite. The more dirty pages we have in memory, the longer it could take our recovery process to come online. So what the recovery process is doing, it's building a in-memory representation of transactions that have been committed, and we haven't yet took those dirty pages and written them out to the data file. And also, it finds the transactions that have not yet committed, and we have to roll those transactions back. And that's the analysis phase. Once the analysis phase is complete, and we have our in-memory representation of transactions that have committed, transactions that have not committed, we're ready to go to the redo phase. The redo phase, as you may guess, is we're redoing the transactions that have committed, but not yet been written to the data file. So I could go and have 100 different updates to a table, they have committed, and those transactions may have not yet been written to the data file. So in this process, I'm going through finding the transactions that have committed, writing those pages out to the data file, and now our data file is in a consistent state with what we have in memory. After that, if I'm in the Enterprise Edition, then my database is online. If I am not in the Enterprise Edition, then I have to wait till the undo process completes. The undo process looks at our in-memory representation of transactions that have not yet been committed, and we have to roll those transactions back. If I'm in Enterprise Edition, I just have a background thread that goes and performs this process. If I'm not in Enterprise Edition, SQL Server has to wait till all of those transactions have been rolled back. Once that's done, my database is online and I'm able to service requests. Write-ahead logging is a protocol that I mentioned before, and basically this protocol indicates that anytime a change occurs in the database, we have to make sure that we write the change to the transaction log file first. Okay? It implements the atomic and the durability property of a transaction, of the four transaction properties. The atomic property basically says, if I have a transaction that has 50 different steps in it, all 50 of those steps have to all occur, or none of them can occur. So it's an all or nothing thing. And we use the transaction log to implement that, because as we're going through the transaction, I write a begin transaction record to my transaction log, other operations have occurred, and then if I perform a rollback, I know all of these steps that have occurred associated with that transaction, so I can undo those transactions. The durability property basically says, once I've committed a transaction to stable media, that transaction is a part of the database, and any other transactions that come through are able to make use of that change that I just made. Like the gentleman asked earlier, it does not necessarily have to be to disk. It can be to battery-backed memory. And in a lot of cases, you'll have a lot better performance from that, but it's not always available depending on your hardware. The checkpoint process. So the checkpoint process is the process in the background that ensures that the redo portion of recovery stays to a minimum. It's basically a process that kicks in every so often, checks to see if there are pages that need to be, and that's the key point here, pages that need to be written to the data file, and if they do need to be written to the data file, it goes out and writes them. It can be very I/O intensive, depending on how many changes that have occurred. The thing with the checkpoint process is it writes all dirty pages that are in the buffer pool. Again, any modification that occur, whether it's a 1 million record table, 1,000 records, it doesn't matter. We have to make sure all the pages for those records that we're changing are in the buffer pool. We will dirty them in the buffer pool, otherwise we'll modify them. We have to latch the page, we change the page, we unlatch the page, and now that page is dirty. If the checkpoint process kicks in, even if that transaction has not yet committed, we'll still write those dirty pages out to the data file. Write-ahead logging makes sure that any of those transaction log records that were generated from the changes that I made, we have to write those out to the transaction log file before checkpoint can write the dirty pages out to the data file. So if I have 1,000 dirty pages in memory, I have to have transaction logs associated with those dirty pages written to my transaction log file before checkpoint is able to write those dirty pages out to disk, to the transaction log file. Sorry, the data file. Can be I/O intensive. Checkpoint never removes pages from the buffer pool. Okay, the buffer pool is this overarching pool of memory that SQL Server uses for pretty much everything, and it will not react to memory pressure. We have a separate process out there called the lazy writer that'll go out and ensures that we have a certain number of free pages available for additional reads from disk into memory. Lazy writer is responsible for removing pages from the data file. The checkpoint process does not remove it. We have a couple of different options for checkpoint. Before SQL Server 2012, we had one option. It was set at the SP configure level or the instance level, and it was called the recovery interval. And the recovery interval basically would allow you to kind of have a little bit of control as to when the checkpoint process would kick in. So recovery interval, again, checkpoint, exactly the same. Checkpoint ensures recovery is kept to a minimum. The default is 0. which means let SQL Server figure out how long recovery should take. By default, it's about a minute, which means that if SQL Server thinks it has enough dirty pages in the buffer pool that the redo process would take more than a minute, it's going to kick in and write those dirty pages out to disk. And that's setting it at the instance level. In SQL Server 2012, we have a new database option called the target recovery time, which allows us to fine-tune when the checkpoint process kicks in at the database level. So a lot more granularity of control now with SQL Server 2012. I can change it with an alter database statement. Here I'm changing it for the AdventureWorks database. I'm setting it to 90 seconds, and then I'm querying the sys.databases view to show you that, in fact, if you can see it on there, that the recovery interval is 90 seconds. Let me zoom in. Okay. Any questions on checkpointing before I get to a demo? Nope? Okay. So in this demo, I'm going to show you how checkpointing works. Before I begin, is anyone not familiar with the sysinternals tools? So the sysinternals tool is a suite of tools that you can go and download from the Microsoft website. We bought them a while ago. It's sysinternals.com. What I'm going to use is a tool called Procmon. And you can use Procmon to capture any interaction between a given process and the underlying disk system. I'm going to use it to capture, let me filter here. Show you my filter. Here I'm going to filter on a certain path, and I'm looking to where my AdventureWorks database data files are living. So my data and my log files are in the same folder here, my AdventureWorks 2012 folder. So any interaction with my data or log files, I should capture it with Procmon. And it's going to tell me how big my writes are to disk and the process that they're coming from and so on, and how many times I'm written to them. So here, and again, I'm going to try to make these available to you if you did want to go and download them. Okay. I'm going to drop my clean buffers. dbcc drop clean buffers is a command to go into memory, and you shouldn't really ever need to run this on a production level system. Takes the data pages that are in the buffer pool that are clean, and in other words, that are not modified, and it flushes them out. Essentially, it's an on-command lazy writer. So I'm going to clear out my buffer pool just so that we're all starting from the same point. And I'm going to set my recovery model to simple. I've not detailed the difference between the different recovery models yet. I'll get to that a little bit later. Just for right now, know that a checkpoint occurs, in the simple recovery model, a checkpoint will cause the log file to be truncated. Okay? That'll make a little more sense in a couple of minutes. So I'm going to set it to recovery simple, and then I'm going to perform an explicit checkpoint. I've already done this, but the sales.salesRow table, whenever you download AdventureWorks from Codeplex, and this is all the examples I'm going to look at are databases that I'm going to create or you can go and download. There's several triggers on this table, and I'm just going to disable them just because it adds to a little bit of confusion here. So drop my clean buffers again. Now I'm going to begin a transaction, and I'm going to update some records in a table. So I'm going to set the modified date where the product ID equals 870 in this table. Okay, so began a transaction, updated some data. Very common. Now my transaction is still live. If I come out to Procmon, you can see that I captured a lot of modifications in Procmon. We can see that I'm reading from my data file. Okay, reading from my data file, coming through, and I'm writing every so often to my log file. I've modified data, but I've not modified anything in the actual data file yet. Otherwise, I would see it occur here. I'm reading the data. I'm bringing those pages that I just modified into the buffer pool, so I have to read them from disk. I dropped my clean buffer, so any of the pages that I would have previously had in memory were out of memory, so now I'm reading them in. So we can see that I'm writing to my log file, but I'm not writing anything to my data file. Okay? Our transaction's still live. I've not rolled it back yet. I've not committed it yet, but we have pages in memory that are dirty. So what I can do is I can look at sysdmos buffer descriptors. This is going to show me all the pages that I currently have in the buffer pool. I'm going to set a filter on it for whatever the table name was that I just updated, plus where the modified equals 1. So I'm going to return all dirty pages that I have in my buffer pool for this table. This update modified around 4,688 records, I believe it was. For those 4,688 records, there were 773 pages read into the buffer pool and dirtied. Okay, so that just means that for those 4,700 records, they exist on around 773 pages. We had to read them all in, and then we had to modify them. Okay, now our transaction still open. I can use sysfndb log. This is I don't know if we've documented this function, but I can use this function where the alloc unit name is this table name to go and find all the log records that were generated associated with that given update. And again, we make a modification in SQL Server. We have to write those modifications to the log file. These are represented as a log record. I can use this function to look at the detail of those log records. We don't necessarily suggest to go and find detail on the log record, but it is openly available should you need to go and do it. Here I have 4,688 log records generated for the 4,688 records that I just modified. So in this case, it's a one-to-one scenario. One log record generated for each record that I updated. Okay, so that's our transaction log file. We can see the detail that way. Looking at the tran count, we can see that I still have one open transaction. Okay. Now I'm going to perform a checkpoint. The checkpoint will look at all dirty pages that I have in the buffer pool, and it will flush those changes out to disk. At this point, if we look back at procmon, we don't have any rights to our data file. I'm going to clear this out. Now, if I perform this checkpoint, I should see now SQL Server's writing out to my data file. Okay. Had dirty pages in our buffer pool related to the update that we just happened. That transaction is still active. We've not committed the transaction yet. Checkpoint takes all dirty pages that we have in memory, writes them out to the data file regardless of whether the transaction has committed or not. And I showed you that, in fact, we are writing to the data file. We wrote probably close to 700 pages to the data file because that's how many pages we had in memory. We may be bunching them up here. It looks like we are. Okay. So now, checkpoint has occurred. I can look back in my buffer pool, run the same query that I have before, and I no longer have any dirty pages associated with that table because checkpoint wrote them out to the data file. Our data file reflects exactly with what we have in memory now, and now those pages in memory are no longer dirty. They're now clean pages. If I was to run a dbcc drop clean buffers, SQL Server would remove those from the buffer pool because they're clean. So now I'm going to commit the transaction. In committing the transaction, let me clear this out again. Committing the transaction just has a little bit of overhead involved in it. Looks like it's just writing it out. Having a rendering problem here. But it just wrote out a record to the transaction log file that indicates that, in fact, that transaction has committed. So all that work had been done before we even committed the transaction. Yeah? So the question was if, I'm sorry.
You said that you wrote the dirty pages out to the data file.
Right.
Doesn't that generate dirty reads from other transactions?
No, not necessarily. Because those pages are already in memory. And so any other server, any other process out there that wants to read those records, they would have to go and read those pages that are in memory. Now those pages are dirty, and that transaction's still open, which means we still have locks on that transaction. So the only way you're going to read those dirty records, essentially, is if you use something like no lock. If you use something like read committed snapshot isolation, you would see a previous version of what that transaction had. Yeah, good question, though. So I've committed my transaction. I think I've committed my transaction. Let's make sure. Okay. Committed my transaction. Now I'm going to go out, look in my transaction log file, and in fact, my transaction log has not been truncated yet. In the simple recovery mode, typically when a checkpoint occurs, any transaction log files that are in the transaction log records that are in the transaction log, we delete them. They're not actually deleted, but we make it so that they're able to be reused in the simple recovery model. We're in the simple recovery model, but the reason those log records are still in the transaction log file is because when I committed the transaction, a checkpoint hadn't occurred yet. So now, as soon as I perform a checkpoint, look at the detail again, and in fact, those log records are no longer there. The reason they're no longer there, the reason they are no longer there is because they are no longer needed. Simple recovery model will never be able to recover to a point in time. So what happens is once we've written the data the data pages that have been dirty to memory out to the data file, we no longer need those log records. Because we'll never need them to be restored to a point in time. So we'll get rid of them. So now I'm going to switch. I'm going to show you the difference between simple and full. I'm going to switch back to full recovery, which is the default for databases when you first create them, unless you modify the model database. I'm going to create a database backup. Here, I'm going to back it up to the null device, just because I don't want to incur the overhead of writing those pages out to the OS. So I have to read all the pages in the database, and once that happens, the operation is complete. So I'm just beginning a recovery fork here. So now I'm going to perform the same update. I'm not going to put it inside a transaction because, as we saw earlier, the transaction doesn't really matter in terms of how the checkpoint operation occurs. We'll perform the same update. We'll go and we'll see that we still have the same number, should have the same number of pages that are dirty in our buffer pool. And in fact, we do have the same 773 pages that are dirty. Come down, look at the number of log records generated. Same number of log records generated, 4,688. We're going to perform a checkpoint. In the full and bulk log recovery models, a checkpoint only writes the dirty pages out to the data file. The transaction log is not truncated whenever a checkpoint occurs in full or bulk log. The transaction log is only truncated in full and bulk log whenever we perform a log backup. Okay. Has anyone here ever ran into problems because your transaction log kept growing and growing and you had to start making more frequent transaction log backups? Yep, that's why. Okay, so make sure we perform a checkpoint. Go look. Checkpoint should have written all of our dirty pages out to our data file. Look in our transaction log. We still have our transaction log records there because, again, in the full recovery model, we only truncate the log whenever we perform a log backup. So I'm going to come down here, perform a log backup, look at the same operation again, and in fact, it has truncated our transaction log. Okay. Any questions? Sure? Yeah. Okay.
Outside of permitting teaching examples like this, why does the checkpoint command exist? Is there any reason you would ever use it in practice?
That's a good. So the question was, other than for what we're doing here, just for teaching purposes, why does the checkpoint process? Why does the explicit checkpoint process exist? If you notice that SQL Server is not kicking in checkpoint often enough, I've seen companies implement a system where they kind of write their own and they put it in a loop or they put it in a SQL agent job. In most cases, it's going to be for scenarios like this, but there are kind of off scenarios where someone has implemented their own because it's not doing what they wanted it to do. So same for a lot of commands. They exist. You shouldn't have to use them a lot. Yeah, they're useful here for what I'm doing now. Great question. Any question?
If you don't have to bulk load, you often want to do a checkpoint before you switch back.
I'm sorry?
If you do a bulk load and you switch from full to bulk load,
Mm-hmm.
load all your data, then you'll often want to do a checkpoint before you switch back to full.
Well, you'll want to perform a. So the question was, if you do a bulk load, so if you're in the bulk log recovery model, and I'll show you an example of this. Bulk log is fraught with peril for a number of different reasons. But he said you would want to perform a checkpoint, and I would say that if you switch from bulk log to full, you're going to want to perform a log backup. Yeah, you want to do a log backup, yeah, and that should take care of a lot of that. Okay. Although a log backup, I would have to test it to see if it actually goes and performs the checkpoint for you. I think there is checkpoint code intermingled in the log backup, but I would have to check the source to be sure. Yes. So the question was, and I do get it to it later. Yeah. So the question was, are we able to see which user made a modification? And we do. And I'll show you an example later of someone dropping a table, and you can go and find out who it was. Yep. Okay, so back to the slides. I have to go through those real quick. Okay, so the recovery models. We've talked about these a little bit. I'm going to talk about them in terms of what happens whenever checkpoint occurs, because that's what we care about for our purposes today. In the simple, the log is truncated on checkpoint, which means checkpoint, again, and I'm going to keep repeating what checkpoint does because it's important and it's kind of a cornerstone of this talk. Checkpoint, dirty pages that are in the buffer pool, we write them out to disk. Once we've done that in the simple recovery mode, because we never have the intent of switching or restoring our database to a point in time, we don't need those log records anymore, so we can get rid of them. Okay? Oh, great question. Right. Yeah, I'm going to get to that a little bit further. But the comment was, if there's a long-running transaction, then even if a checkpoint occurs, we're not able to truncate those log records. Absolutely right. So if the bets are kind of off if we have long-running transactions because they won't allow us to truncate regardless of the recovery model. Okay. In the bulk logged and the full recovery models, the only way that we'll make our log space available for reuse is if we perform a log backup. So when a checkpoint occurs in bulk logged or bulk logged or full, then we're not going to truncate our log. We only truncate the log whenever a log backup occurs. Okay. And those of you who raised your hands earlier and were talking about ran into problems, the transaction kept growing and growing and growing. Could have been due to the fact that you had a long-running transaction and you couldn't truncate the log, or the fact that you just weren't completing log backups quickly enough.
What's your best practice recommendation for how often to do a log file backup?
Great question. The question was, what's the best practice? And unfortunately, it depends. So it depends, and the reason I say it is, it depends on your application. So if your application is generating a lot of transaction log records, then you're going to probably need to perform log backups more frequently to make sure your log doesn't grow. Also, it depends on your recovery time and your recovery point intervals. So if you want to make sure that, say, you have a hard limit that you don't want to lose more than 5 minutes worth of data, so you have an explicit need to be able to recover to a point in time, then you're going to need to take log backups every 5 minutes. And I would say that is the more important of the two scenarios, because it depends on how much data the business is willing to lose. Right? So, great question. The full recovery model is the default recovery model. If you are in the full recovery model and you do not take transaction log backups but maybe once a day, and you only take transaction log backups so that your log file doesn't grow out of control, then it's time you switch your recovery model to simple. Life is going to be a lot easier. It's one of those things where the full recovery model is the default, and that's kind of unfortunate because a lot of shops don't need to restore to a point in time. They're doing nightly backups, and that's all they do. All they want to do. In that case, switch to simple, and your life's going to be a lot easier. The bulk log, and I mentioned earlier that it was kind of a fickle beast because it can prevent you from being able to restore to a point in time. But I'll get to more detail on the bulk log models here. Sure. Mm-hmm. It goes off the model. So if you switch your model, the question was, that's not actually, it depends on what recovery model your model database is in, and it's in full by default. If you switch it, then any new databases will be in simple. Yep. Transaction log backups, just kind of a refresher. These are taking log records that we no longer need and fleshing them out to a data file. Now this happens, the actual truncation of the log happens on a VLF boundary, and I'll talk about what VLF boundaries are a little bit later. But transaction log backups basically make it so that we can reuse portions of our transaction log. Used in conjunction with a full backup, once you've completed a full backup, you can take transaction log backups forever, and you never have to take another full backup. I don't suggest that, but as long as you have an unending chain of log backups, you can restore your database to a point in time. You're going to be better off taking full backups incrementally or file group backups and restoring those so you don't have to restore thousands of transaction log backups. You could do it, but you don't necessarily need to do it. Not available in the simple recovery mode because simple recovery mode, checkpoint occurs, we're going to get rid of those transaction log records because we don't need them anymore. A transaction log backup will never shrink the log file. The only thing that ever shrinks the log file is you doing a DBCC shrink file. A log backup only makes it so that we can reuse portions of the log that we no longer need. Okay. So the bulk log recovery model. This recovery model is in effect so that we can perform certain operations more quickly. And there are a finite number of bulk logged operations that we can perform out there. So index rebuild is one of them, a select star into table. There's a number of other bulk logged operations. And essentially the idea behind a bulk logged operation is that I'm writing less to my transaction log file as the operation occurs. Okay? So for example, in an index rebuild, switching to the bulk log, we write less to the transaction log file as the index rebuild occurs, but whenever I perform the actual log backup, we have to go out, find all the pages that were touched by that index rebuild, and we have to include all of those in the log backup. So it doesn't make our our backup file any smaller, it just makes the operation a little bit quicker. The caveat to that is that because of how write-ahead logging works, I have to make sure, because I am writing less to my transaction log file, I have to make sure that any change that I make, I'm writing my log records out to my log file, but I also have to write to the data files before the transaction completes. So depending on the operation, it could make the operation slower. So it's one of those things where it depends, and you have to test it. In most cases, you're going to get a gain because I'm writing far less records to the transaction log file, but you have to test it. Okay, so let's take a look at a bulk logged operation. Doing okay on time. So I'm going to look at two scenarios. I'm going to create these databases on the fly, one called minimal logging data, and I'm going to set the recovery model to bulk logged. And then I'm going to begin the recovery chain. It does not matter if I am in the full or the bulk logged recovery model. If I have not yet performed a full backup, SQL Server behaves as though that database is in the simple recovery model. It only starts whenever I perform that full backup. So if I don't perform a full backup here, then whenever a checkpoint occurs, we're going to truncate the log. So I have to perform a full backup. Okay. Use minimal logging, and then I'm going to look in my log file right now, and I have just around 10 transaction log records in there, mostly associated with the creation of that database. Okay. I'm going to create a heap table. And then I'm going to insert 5,000 records in my heap table. I'm just going to pull from my sales order detail database from my my sales order detail table from my AdventureWorks database. Insert 5,000 records. Then I'm going to go look in my log file for the heap table, and I can see that I have around 5,000 records and some change. So for every record inserted, we generated a log record to go along with that record that we just inserted. I'm going to perform a checkpoint. So I'm going to take all my dirty pages that I'm going to flush them out to disk. I'm going to look again. My log records are still there because I'm in the bulk logged recovery model, and I've not performed a log backup yet. So I need to perform a log backup. Performing a log backup, we can see that, in fact, our log file is now truncated, which is what we'd expect. Now what I'm going to do is I'm going to use a tab lock hint. Performing a tab lock hint while inserting into a heap table makes it a minimally logged operation if I'm in the simple or the bulk logged recovery model. Okay? So I'm perform the same operation before. I'm still going to insert 5,000 records into the table, but I'm going to use the tab block hint, and this ensures that no other process is going to be inserting into that heap table while my process is inserting into it. Doing that, still have the 5,000 records inserted. Looking at the number of log records generated, 35 log records generated for this operation as compared to the 5,038 that we had before. So much more minimally logged because I'm only tracking the fact that I'm changing allocation pages. Allocation pages are a talk for a different session other than this one today. But they basically keep track of what pages belong to what files and so forth in SQL Server. So that's a minimally logged operation on a heap table. I can perform a minimally logged operation on a clustered table. I'm going to perform essentially the same scenario that we just looked at. Get rid of that session, just in case. Switch to the bulk log recovery model, perform a database backup. I'm going to come down here, I'm going to create a clustered table. SQL Server, two different types of tables. You have a heap table or a clustered table, and they are mutually exclusive. Here, I'm going to create a heap table at first, and then I'm going to cluster it, which basically orders it. Now, I'm going to perform my insert into my clustered table, look at the amount of log records generated, and I can see that I have, as it turns out, more log records generated here than in my original insert into my heap table. So there's a little more housekeeping to be done whenever I insert into a clustered table, even though that my clustered index is on a increasing field. I'm going to perform a log backup to truncate what we've done in our log file, make sure that we write all that data out to disk. Now I'm going to perform a truncate table. Truncate table is one of those things where it's always fully logged. So a truncate table is a fully logged operation, but the way in which truncate table works, it always logs the least amount possible. So perform a truncate table, and I can see that the way truncate table works is it just goes out and it deallocates allocation pages. So it doesn't actually go through and delete all the records in the table like a delete statement would do. So it works a little bit differently, and it's actually a DDL operation instead of a DML operation. Okay, oops. So now look at we've just looked at the log file. To perform a minimally logged operation on a clustered table, I need to turn a trace flag on. It's trace flag 610. Perform a log backup here to truncate the log that I currently have. Now I'm going to try to insert the same operation as before after I've turned that trace flag on. Looking at the amount of log generated, I have 496 log records generated here as compared to the 5,100 or so before. So not quite as minimally logged as inserting into a heap, but still much more minimally logged as concerned when I didn't have that trace flag on. So that's the benefit of the bulk logged recovery model. The problem with bulk logged is that if I take a log backup, then I perform a bulk logged operation and my database goes down, I won't have the ability to perform a tail log backup. So the best I can do is restore all the way up to when my last log backup occurred. So that is kind of a downside of the bulk logged recovery model. In bulk logged, once I switch to bulk log, you never want to keep a database in bulk log just for that particular purpose. Because if you're in full and you switch to bulk log, you're in full because you intend to restore that database to a point in time. So you switch to bulk log, perform your bulk logged operations, whether it's an index rebuild or whatever, perform that, switch back, then take another log backup. That's the protocol there. Okay, turn my trace flag off. Any questions on that? Nope? Okay. Moving right along.
Before you go on,
Sure.
can you recover from the bulk log? Can you recover your database from the log that's logged and save the bulk log?
So the question was, can I recover my database if it was in bulk log? Sure, you can. But the reason I mentioned this before is I'm not going to be able to recover it to up right before the disaster occurred, right? So if I take a log backup and then someone out there performs a bulk log operation or whatever, I'm still going to have to perform all my restores.
So you're going to lose, what I'm saying is you're going to lose the bulk log activity.
Yeah. Yeah, you're going to lose the bulk logged activity because the best you can do is restore up to the point in which you took your last log backup.
So why do you have it?
You have it for performance purposes, but once you perform your bulk logged operation, you need to switch back to full and then take your log backup. Right? You never want to keep it in bulk log. You have to perform a little maintenance. You have to explicitly switch it to bulk log, do what you need to do to make it faster, your operations faster, and then switch back to full. Oh, so you can roll it back. You can roll back a bulk logged operation. So we have to keep track of those. We're just keeping track of that the allocation pages have changed, and that's the benefit of it to make it faster. If you want to talk more after the talk, I'm happy to talk to you more about it. Okay, so I apologize for the kind of intrusive orange color here. So transaction log components. We're going to talk about logging behavior a little bit more, talk about log records in a little more detail, log blocks, basically the components that make up the transaction log. I'm not going to talk about the log pool today just because it's a little bit outside of what we're going to talk. Log pool is a new feature in 2012 that basically makes logging a little bit faster for availability groups. So the way that the transaction log works is that we're expecting finite growth. It's a circular file in nature. So we begin at one end, and we're logging records, and we're going to hit the end of the file eventually, and if we've done our due diligence, we should be able to wrap around all the way back to the beginning. So it's circular in nature. Data files, we can expect to grow forever. Data files are not circular in nature. Log files, circular, we write to a certain point, we're always writing to them sequentially. So even if I had 2 or 3 different log files, I'm always going to write to one file sequentially, get to the end of that, come over to the second file, write to it sequentially to the end, and then loop back around. So the architecture of it works the exact same way. No, you're going to write to the end, and then you'll wrap back around. Yep, I have an example I'm going to show you. Yep. So if you're a DBA, or your DBA is directly responsible for how this log file is managed. Okay? If you don't expect to ever have to recover to a point in time, switch to simple, and life's a lot easier. If you have to recover to a point in time, you have to make sure that transactions out there aren't long running, and you need to make sure that you size your log file appropriately. A log record, as we've looked at so far, is an atomic change in the database. So in our first example, the first demo, I updated 4,700 or so records, give or take. Each one of those records that we modified generated a log record. So we wrote all those files out to the transaction, or all those modifications out to the transaction log. A log record is not necessarily associated with a committed transaction. It's just committed with a change in the database. Okay, so one transaction could have hundreds of thousands of transaction log records, and that transaction doesn't yet have to be committed. It's just an indicator of what has changed. Okay, and we write it out to the transaction log. Log records contain information to redo or roll back a transaction. For example, if I'm performing a modification and that modification takes locks, we keep track in the log file which locks were taken so that if we have to roll that transaction back, we know exactly which locks to take in the database. So it contains information to perform the redo or the rollback. Sure.
When you talk about redo and reflection, what exactly happens on an update? Update a record that's already in the database. What are you doing in the SQL Server to reflect?
Okay, so the question is kind of what's the lineage when an update occurs, right? So in the example that we looked at before, we updated a record, we updated one field to the current date for a certain product ID. So the way that works is we have to go and create an execution plan to figure out how to go and grab the data. We're going to execute the plan. The plan's going to go out and check what's in the buffer pool. So buffer pool is a big overarching pool of memory that we have in SQL Server. So we know about where in the buffer pool these pages should be because we have the database ID, we have the file ID, and we'll have the page ID. So those are all hashed to a specific value in memory. If they are in the buffer pool, great, we'll update them. If they're not in the buffer pool, we have to go out and issue an asynchronous I/O to go and pull it from disk. So if that happens, our process that's on our scheduler has to basically take itself off the scheduler, wait to get that I/O back, pull that data into the buffer pool so that we can latch it and update it. As we're doing that, as we're making the changes to those pages, we're writing log records out to a portion of memory called a log buffer. So we're writing log records as we're modifying those pages. As that transaction commits, or we hit a 60K limit, and I'm actually talking about this in this slide here, as we hit that, either that transaction commits or we hit that 60K limit, we have to flush those log buffer records out to the log block on the transaction log file. Once that occurs, those log records are persisted, and as soon as that transaction commits, we write the rest of the log records out, and that update is complete. Okay, so that's kind of the lineage of how that occurs in SQL. Did that answer your question?
I'm not sure.
Okay.
I think what he's asking is, does it keep load value also before and after in the log logs?
We keep enough information so that if we need to roll that operation back, we'll be able to do that. Yeah, so we keep that information in the transaction log file. We'll be able to infer it. That is for the server. Yeah, so that's a portion of the buffer pool, and that's kind of the overarching thing for the. Yeah, the server instance. Yeah, so if you have multiple servers, then you'll have multiple buffer pools. Yeah. If you want more information, come up after the talk, and I'm happy to explain it further. So a log block, I just explained it a little bit. Log block, as transactions are modifying pages in the buffer pool, we're writing them out to basically, a portion of memory known as a log buffer. And a log buffer is anywhere from 512 bytes to 60K in size. So either a transaction commits and we flush that log buffer out to a log block on disk, or we hit that 60K limit. As soon as we hit the 60K limit, we have to flush those log records out to disk. Okay. The closer we get to 60K, the better performance we should see in terms of writing those out to the file. And I'm getting a little bit short on time, so kind of hold your questions till the end. I only have about 20 minutes left because I want to get through most of these demos. In the demos, I'll show you how that writes occur, and the transaction size that you write does matter. Okay. A virtual log file is the unit of truncation of the log file. So a transaction log is made up of multiple segments, and these segments are called virtual log files. A virtual log file is generated whenever we first create the file and anytime we grow the file. So here I have a chart, and it shows you based on whatever the size of the growth of the log file and the initial file size. Anytime we grow it, we add a certain number of VLFs. Now, the reason I want to talk about this is because if you have too many VLFs, it's known as VLF fragmentation. And the processes that read from the log file, recovery, database mirroring, CDC, transactional replication, the more virtual log files they have to read through, the slower those operations are going to be. For example, I had a client 2 years ago. They were running database mirroring, asynchronous database mirroring, and they had their growth on their log file set at 1 meg. Okay? They had a very long-running transaction, very long-running, and they weren't maintaining it. And come to find out, there was a non-yielding scheduler on the thread that was running database mirroring. So the mirroring was backing up because there were so many virtual log files. 980,000 virtual log files. We'll alert you now if you have over 10,000 in SQL Server 2012. So 980,000 virtual log files, they failed the server over. It took 18 hours for that database to come online. So the more virtual log files you have, the more of a problem you could potentially have. And as your log file grows and grows and grows, you add more and more and more virtual log files. So that's something that you have to keep in mind. Virtual log files, again, created whenever the file was created, anytime it grows. How many virtual log files do you need? It kind of depends. Too many, it's a problem for recovery. Too few, and you're not going to be able to effectively start truncating those virtual log file segments. So we try to say anywhere between, and it's database dependent, anywhere from 100 to, if you start getting closer to 1,000, we'll start fussing at you a little bit. If you call me and I see a couple of thousand virtual log files for a database, I'll say, hey, you probably need to maintain this because if you were to have to fail over, it may take you a little bit longer. Probably not with a couple of thousand, but to be safe, we try to tell you to keep it under that. In SQL Server 2012, we will actually throw an error, or at least a message in the error log telling you that you have too many log files on recovery. The alert will tell you that you have 1,000, but it's actually 10,000. I had to research this a while ago. They've probably fixed this by now. But the thing to take away is that we'll let you know if you have too many VLFs because it's something you should take a look at. A log sequence number is essentially a unique identifier or an identity column for a log record. It's something to identify a log record. It's monotonically increasing, and it's a three-part name. So it's your virtual log file number, it is your log block number, and it is your log record number. So here we have an F sequence number, we have an F sequence number of 38, and that's in decimal. If we relate it over to the log record that we have from FNDB log, it relates to 26, and that's 26 in hex. So any questions before I dig into a demo? We have about 15 minutes left. So I'll get through these as fast as I can here. Okay, so here I'm just going to show you the circular nature of the log. So I'm going to come through, create a database. As soon as that gets finished, I'm going to set the recovery model to full. And then I'm going to create a database called sales. Okay. Now, I'm using dbcc log info, and that will return to me one record for every virtual log file that I have in a database. A couple of things to keep in mind here. The F sequence number is the virtual log file number, essentially, and there's a status and a parity bit. This parity bit is always either 64, 128, or 0. We will never use instant file initialization for the log file, okay, because we have to zero it out because that tells us where the end of the file is. So we're using 64 here, and 64 just tells us that this file is currently in use. A status of 2 means that it is active. So these three virtual log files are essentially inactive currently. So we haven't written any log records to those log file segments. Okay. So now what I'm going to do is I am going to expand that here. And I'm going to insert some records into my sales table. Ran that insert 100 times, dbcc log info, and now I have another virtual log file that is now active. It's still 64 and our status is 2. Let's run this again. Log info. Now something interesting has happened here. I'm in the full recovery model. Our status went from 2 to, now this is 2 and these are 0. Does anyone have any idea what may have occurred? Exactly. Very, very good. I'm in the full recovery model, but I have not taken a full database backup, so we behave as though we're in the simple recovery model. Yep. So what is that indicating? I'm getting ready to show you. So this is essentially our first VLF now, because what has happened is we've wrapped back around. Okay? So we were writing here, and our status here is 0 because we truncated it because we were in the simple recovery model, essentially. I've taken a full backup now, so now we're in the acting full. So 64, 64, 64. Now we have wrapped back around. And notice that we went from 31, 32, 33, we wrapped back around, and now we're at 34. Okay? We're able to wrap back around because that truncate, because the checkpoint occurred, that truncating of those log files made it so that we could reuse that log file segment. So now, if I insert some more records, this is going to change to 128, and that status is going to change to 2. And if I insert enough if I insert enough log records, we're going to have to grow the file. Okay? So let's see how that works. So insert some more records. Do it a couple times here. And now, sure enough, we generated, we grew the file. Yep.
There's still one open transaction inside the virtual log file. It cannot be read.
Right. Right. It cannot be used.
Then if we jump over it and jump to the next 3.
Exactly. We'll have to grow it. So the question was, if there's an active transaction, we can't reuse that VLF segment, and exactly, we'll have to grow the file and then reuse it. Okay? Okay, so for brevity's sake, I'm going to skip past this, and I'm going to go to the VLF growth. So here, I am going to create another database called VLF growth, and I am going to create it here, and I'm going to create an initial size of 1 megabyte. Okay, you would never do this in a production system, but this is just for fun, right? So here I'm going to create just a temp table called log space that I'm going to dump some information into. I'm going to call dbcc SQL perf. I'm going to pass log space to it, and then I'm going to select from it. You can see here that my log file size is initially 1 meg, and it's 36% used, which is about average since we've not done anything with the file yet. Okay, so now I'm going to come down here. I am going to dump dbcc log info into this table, and I can show you with this calculation the size of each one of those VLF segments. Okay, so we can see that our initial size was 1 meg, and each one of those VLF segments is around 1/4 of a meg, give or take. Now, if I want to grow my file, here I'm going to come down here, I'm going to modify the file, I'm going to set it to a size of 100 meg. That doesn't mean that I'm adding 100 meg to it. That means, I want the file size to be exactly 100 meg. Okay, so run this. We grew it by 100 meg. Looking at the file again, we can see that, well, you can't see too quickly, but if I open up calculator here, if I do 12.375, and there are 8 of these, I can see that it added, too many zeros, but it added 99 meg to my file. Okay, so it grew it by 99 meg, and each one of those new virtual log files that I added, because I added 99 meg essentially, I grew it by 8 VLFs, and each one of those is 1/8 of the entire file size that I added. Okay. Any questions there? All right. Okay, so let me come down here. So why is my log file getting so large? Well, it's usually one of just a few different issues. We have a long-running transaction that no one has finished, and that in doing that, I can't reuse my VLF boundary, so I have to keep growing my file. It often results from being in the full recovery model and not taking frequent enough log backups, or being in any recovery model and having a long-running transaction. The resolution: fix the underlying problem, whether that is commit the transaction or just start taking more log backups, more frequent log backups. Shrink the transaction log file down to a minimal size, and then grow the file back out in a certain number of increments so that you get a good number of VLFs, but not too many. And in this case, you have to kind of just test around and see what works for your environment, because your log file needs to be big enough so that it can accommodate your largest transaction, but you don't necessarily want it too big and there be too many virtual log files. A VLF can be reused if there are no active transactions contained in the current VLF or previous VLFs, and there are no unreplicated transactions. So anything that uses the transaction log file, such as mirroring, availability groups, CDC, not log shipping, but transactional replication, need those log records, and if they've not consumed them yet, then you can't get rid of those log records either. Hold your question for right now, because I want to try to get to the end of this. Come up after, and I'm happy to answer them, because I'm running a little bit low on time. Otherwise, if I'm the simple recovery model, I truncate the log on checkpoint so I can reuse those boundaries, assuming that I don't have active transactions that need, or unreplicated transactions. Otherwise, it occurs at a log backup. I can use the log reuse weight description field in sys.databases to find out why my log file is not being reused. In most cases, you'll see either checkpoint or active transaction, but the other options are up there for log backup, database snapshot creation, and so on. So that's going to be the first place that you're going to want to look to see why your transaction log is not currently being reused. If I need to shrink the transaction log, I'm doing this to reduce the size of the transaction log. So this is the only way to reduce the number of VLFs that you have. Right? Doing a log backup does not reduce the number of virtual log files you have. The only way to do that is through a shrink. We always shrink at a VLF boundary, and I would suggest you use dbcc shrink file as compared to any other method like a shrink database, because you only want to shrink the log file. There's no reason to shrink the database itself. Okay. Once you shrink it, grow it back out to the proper size, and then you should be done. Okay, so let's take a quick look at virtual log file fragmentation. This will be a really quick demo here. Okay, I'm almost done. These other scripts that I had on here were just in case we had more time, but I'm almost to the finish. So what I've already done here is I've created a database called full log. And I did this beforehand because it took a while to grow it out. So if I come down, it's in the full recovery model, and I've done a database backup. And basically what I did was I inserted into the table a certain number of records into the table, and I did it 80,000 times. If I look at the number of log files that I have in this database, I currently have around 12,288 virtual log files in this database. And we can see that the status on all of these is 2, so they're all active. Okay. So what I want to do, and I can query this in sysdm io virtual file stats to show me the actual size of my transaction log. Here it is 3 gig, and if I look, that's the initial size that I created it to. So a max size of 3 gig. So what I'm going to do is I'm going to take the database offline. Just going to take it offline. It should be a really quick operation, maybe. Now that I say it's quick, it's going to take a little bit to take it offline. There we go. So the database is offline, and now I'm just going to bring it back online. 12,000 VLFs in this database, and it usually takes about a minute to bring it online. Now I wouldn't necessarily say that is a linear operation. So the more VLFs you have, the more it's going to take. So it's not, unfortunately, not a linear growth. It's more, I wouldn't necessarily say exponential growth, but the more operation that it has to basically the problem is having to read through all those virtual log file headers, and the more work that it has to do, the longer it's going to take. So this should take about a minute. And once it comes back online, they're around 30 seconds, so that's nice. There are a couple of ways to handle this. I could take a log backup. In this case, that's going to take a long while. But what I'm going to do is I'm going to break the chain. I'm going to switch it to the simple recovery model. And that's really quick. As soon as I switch it to the simple recovery model, do a dbcc log info, and then all my statuses, I need to switch databases here. All my statuses went from 2 to 0. So all those log records are able to be reused. So I switched to simple, and now, since I've switched to simple, I've broken my recovery chain, which is not necessarily a good thing. So I need to switch back to full. Once I switch back to full, I can still go and look at the number of log files I have, the same number I had before. I want to shrink my file, so just specifying the file size of 2 says shrink the second file. The log file is always the second file in the database. So I've shrank it down, and now what I'm going to do is I'm going to perform a differential backup, and that will bridge my chain because I switched from full to simple back to full, and creating a differential backup will bridge that recovery chain. Okay? So I don't have to necessarily take another full backup here. A differential is fine. I'm not going to do it in this case just for brevity's sake. 2 minutes left. I'm going to go to the example where we look at which user dropped a table. And then if I can get through the rest of my slides, they're just kind of auxiliary slides. So what I'm going to do here is I'm going to create a table called dropped table DB. Aptly named because we're going to drop a table in it. Create a database, real simple database creation. I'm going to set it to simple. I'm going to create a table called important table, and I'm just going to dump some records into the table. Perform a checkpoint, and then something happens and someone comes through and they drop this table. Now before, it would have been a little bit of a painful exercise to go and figure out who dropped that table. Now that you're armed with all this fancy transaction log knowledge, you can easily go and find it. Because what you'll do is you'll go look in sysfndb log. You want to look for a transaction name of drop obj. There's only going to be one in this case because there's only one drop occurred. So this is the transaction log record associated with that dropped object. It's easily discernible here because that's the only drop that occurred. I could do additional filtering if I really wanted to. But the thing to look at here is the transaction SID. This is the security identifier of the user that actually performed that operation. So if I copy that and I come down to sys.server principals, paste that in here, I can see that my user was the one that actually dropped that object. So an easy way to go find someone who dropped a procedure, dropped a view, dropped a table, so on. Okay. Just real quick, log wait types. If you are going through and you're trying to find a problem with writing to the transaction log. If you have one of these two wait types, the write log is I'm not able to write transaction log records to my file fast enough. Okay, so that I could have a bottleneck on disk, so I want to go look at disk latency measures to see why I'm not able to write to my log fast enough. I could just not have enough enough IOPS to be able to write to it for whatever I'm doing. And then log buffer is I'm memory bound. So I have a little bit of memory pressure and I'm not able to write those log records in memory fast enough. It could also be associated with not being able to write to disk fast enough, but it's usually either a memory or a file related issue, and most likely in most cases it's going to be not being able to write to my transaction log fast enough. Okay, so that's all I have. I am out of time. If you have any questions, I'm happy to answer them for as long as you'd like. Thank you for coming. Please fill out the evaluation. Thank you.